This is section 2.1. This is the start of our Module 2. Module 2 is very long, so it's likely we'll be here all the way till Halloween, if not beyond. So it's got lots of meaty information, and each day you'll be given notes regarding the task and homework to complete. So this is the start of getting into some really content material of quadratics. So some required prerequisite knowledge is the formula for the area of a square. If each side of the square is x, then side squared, length times width, is x squared. You could see that quadratic in there. What if we increase, that means to add, onto the length of each side by 3 units? That means this side would become x plus 3, and this side would become x plus 3. Then what is the area of the square? Then the area would be x plus 3 quantity squared. Now in Module 1 we would have FOILed that out, but right now we're just representing the area. What if we make the side 3 times as long? That means to multiply of its original length. Now what is the area? You're probably starting to get pretty quick here. 3x squared. Now what if we take the area of the square and multiply it by 5? So the area of the square, the original square, was x squared. Multiply by 5 means exactly what it sounds like. So we would have 5x squared. And how about if we increase the area of the square by 3? So this is the area of the square. Increase is to add. So increase by 3. So these are key words and key phrases that you have to look out for. The task. Okay, now I know it's been a while since Math 1, some of these names, Tia and Tahani and Carlos and Clarita. Here, a lot of this module is Optima Prime, is designing a robot quilt for her new grandson. She plans for the robot to have a square face, so there's that square again. The amount of fabric that she needs for the face will depend on the area of the face. So Optima decides to model the area of the robot's face mathematically. She knows that the area A of a square with the side length x, which can be inches or centimeters, it could be anything, is modeled by the function. Now remember, we talked a lot about function notation. A sub x is A, like the function at x. X is the input. The area of x is the output. So input is inside the parentheses, output is the whole thing. What is the domain of this? So talked a little bit about domain in Module 1. Domain is the input. Well, what can I put in for the amount of fabric? Obviously it makes sense that it's only going to be positive values. Okay? And 0 is not included, because it wouldn't make sense to have 0. There wouldn't be a quilt. So that is intentional, that it's a parentheses. It is not included. So I would love it if you paused the video right now and thought about each of these, what these matching would be. And then I would see you after you pause. Welcome back. The length of each side is increased by 5 units. So I demonstrated that on the front. That would be B. The length of each side is multiplied by 5. C. The area of a square is increased by 5. Area increased by 5. And the area is multiplied by 5. All right, Optima started thinking about the graph of y equals x squared in the domain of all real numbers. So if you remember a little bit of our basic quadratic, that's the perfect squares. just a parabola with the vertex at the origin. And wondering about how changes to the equation of that function, like adding 5 or multiplying by 5, affect the graph. She decided to make predictions about the effects and check them out. Now, again, in person, I would have graphing calculators and we would explore this. So I do have an exercise for you tonight where you're going to explore. So I call this the parent function. The parent function is what happens to the function without any transformation on it. This is the graph of the parent function, and that is the function itself. So y equals x squared is the parent, it's the basic function without any transformations. Transformations are what we're doing here, adding, multiplying, etc. So if you use your graphing calculator to graph each function one at a time in the same window, how is each graph the same as y equals x squared, and how is each different? So I hope you've dusted the cobwebs off of this puppy that we used a fair amount of times in Module 1, but we'll use it quite often in Module 2. So if I type in the y equals x squared, so there's the parent function. Now I'm in an old window because I teach AP statistics, so that is going to change a lot of my graphs. So I always have to turn off my stat plots, and you may have to do that too, and hit zoom 6 to put you in what's called a 10 by 10 window, and then you'll get the graph. So this is the parent graph in blue. If I do one of those transformations, y equals 5x squared, x plus 5 squared. Now, for sake of our short 35-minute class this year, I'm going to put all these in at once. I hope you can pause the video, put these in your graphing calculator so that you can compare with me now. I'm in the sun here. And no one's here to shout, although most people don't shout and unmute anyways. All right. Okay, so I hope you have unpaused the video, and this may be tough to see all at once for you. Obviously, it's a little bit like a cooking show for me in terms of knowing what's the end result is. But for time's sake, you could watch this again, try these again, and graph them one at a time. So what this does when you multiply by 5 is they have the same, some of the similarities are the same x and y intercepts. And one of the differences is it's skinnier. Skinnier. We call that a vertical stretch. This here, it's the same size. So on the left here, just in case you missed that, are similarities. On the right are differences. And this graph is this guy here. So it's moved 5 to the left. We call that a horizontal. Horizontal is anything left and right translation. 5x squared. So you have a couple choices here when you are comparing. There's a difference. This is 5x squared, whereas 5x in parentheses is actually 25x squared. So that's going to get super skinny for its difference. Well, I'm going to let you just get away with that. Super skinny. Because this is 25x squared. So that is going to really take off quickly. and they have the same x, y intercepts. And x squared plus 5 is this one that's shifted up. So it's the same size. It's a shift up 5, and we call that a vertical translation. Translation is a slide left or right or up or down, whereas a stretch and a shrink, we didn't do one with it's a shrink. A shrink, just FYI, a vertical shrink would be one like y equals, say, 1/3 x squared. That means it would grow really, really slowly. So you've got vertical shrink, vertical stretch, horizontal translation. Typically you have to say the direction. So that's why I said 5 left and up 5. So this is always important when you're defining the characteristics of the translation. Again, if you have to pause the video, please do so. All right, here's some pretty graphs. All right, so create a table and a graph for y equals x squared. I hope by now that you know that this is the perfect squares. So if I do -3, -2, -1, 0, 1, 2, 3. This is again called the parent graph. All right, this basic parabola, P-A-R-A-B-O-L-A, with these points is very, very, very important. Should I put a third? Why not? I-M-P-O-R-T-A-N-T. On one of the quizzes, I'll ask you what one of your biggest pet peeves is. And one of my students once said when people say important with like a D instead of a T, like important. And I never really thought about it, but once that person pointed it out, it sort of made me laugh how many people say important. And there was lots of other pet peeves on that quiz, you know, from loud gum chewers to people who step on the back of your shoe. One girl said when people say YOLO all the time, oh, I failed the test, YOLO. But that one made me chuckle. A lot of them make me chuckle because I realize just things that annoy people. It's really funny. A pet peeve is just that. It's like an annoyance. Okay, now -3 squared is 9. 2 squared is 4. -1 squared is 1. 0 squared, 1 squared, 2 squared. So this is the parent graph. And this is very, very, this deserves glitter. Very important. Okay, so we'll graph it. Kind of getting sick of my red, but so 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Are you joking me? I had all that room and I didn't go down. 1, 2, 1, 2, 3, 4. -1, 1, 0, 0, 1, 1. Reflect, reflect. Now when you connect, make it nice and pretty, just like your math teacher. It's nice and curvy. It's not pointy. It's a U shape. It's not a V shape. We're actually going to do a graph that makes a V shape called absolute value. And put arrows on it, please. It goes to infinity. The domain is all real numbers. Let's practice that. And the range in this case is 0 included to infinity. Okay. Create a table and a graph for y equals x squared plus 2. So we are going to, you could put this on the calculator, but what I want you to think about is the same input values. And now I'm going to make my ruler a little bit shorter so I don't go off the grid again. Okay. Now, the old output was 9. You can probably imagine that this affects the output. So this next output is going to be 11. 6, 3, 2, 3, 6, 11. So I added 2 to this output. Your other choice is to go to your graphing calculator and add it. So if you use your graphing calculator, you would just type it in as such and then go to the table. Okay? But what I really want you to start to see are these transformations. What does it mean to add 2 to the original output? That's why this parent function is so important. Okay, so 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 2, 1, 2, 3, 4, 5, 6. Negative 1, 1, 2, 3. 0, 2. That's typically the points that people compare are 0 and 1. Alrighty. Nice pretty U-shape, arrows. Yay. Okay, x squared minus 3. X, f of x. I'm going to keep using these same basic points. This is a little bit cut off on my paper. Now, remember, I'm thinking of the parent. How does it compare to the parent? The parent original output, 9410149, you're going to subtract 3. 9 minus 3, 6. 4 minus 3, 1. 1 minus 3, negative 2. 0 minus 3, and then they're going to repeat. I hope that you're starting to see that repeat concept. All right, now this is a shift down. I should really get a ruler in. Okay, negative 3, 6. 1, 2, 3, 1, 2, 3, 4, 5, 6. Negative 2, 1. Negative 1, negative 2. 0, 1, 2, 3. Now again, in this setting, anytime you want to pause this video, please do so. So let's take a look at this. We look at it from the parent graph. Let me zoom out a little bit. I think I am zoomed out. Okay. So the parent graph has its original, this is called the vertex, that beginning point there. So the graph is the same for equations in the form x squared plus k. The graph is the same as y equals x squared, and it is shifted k units in the same direction as the sign. All right. So that's important. You're going to find that the input is the opposite, but the output is the same. The graph is the same as y equals x squared, and it is shifted k units, in this case plus 2, in this case minus 3, in the same direction as that sign. This was shifted up 2, this was shifted down 3. Okay, now I'm just going to repeat the parent graph here for number 7. You're going to be a parent graph expert. -3, -2, -1, 0, 1, 2, 3. -3 squared is 9, 2 squared is 4, 1 squared is 1, 0 squared, 1 squared, 2 squared, 3 squared. Now, granted, you could go pick any 6 numbers, but obviously we're going to go hovering around the origin. Okay. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And reflect, you could choose whenever. 1, 2, 1, 2, 3, 4. Ba, ba, ba. -1, 1, and 0, 0. Now, after a while, you won't even need a table for this. You will just know the parent graph table. Okay, so now we're going to create a table. Now, I sort of gave it away, right? This is inside the parentheses. So it is going to affect input. So this is where the shift left or right comes from. Okay? So, x, f of x. Now, what I'm shifting or plugging in is this into the input. -3 plus 2 is -1, squared is 1. -2 plus 2 is 0, squared is 0. -1 plus 2 is 1, squared is 1. 0 plus 2 squared, 1 plus 2 squared, 2 plus 2 squared, etc. Now you're going to find that they didn't have the same effect as adding or subtracting to the outside, and you would be exactly right. So, -3, 1, 2, 3, 1, -2, 0, -1, 1, 0, 1, 2, 3, 4, 1, 4, 5, 6, 7, 8, 9. I'm going to stop there because these are going to reflect. These next are going to be off the grid. We're not going to graph those. But what, oopsies, I missed. What you're going to find is that once you find that vertex with that symmetry point, you can start to repeat. All right. Now, this, if you're comparing the parent, here's the parent. Let's star that again. Parent, that's without transformation, the original, the OG. This is a shift left 2. But notice, inside is +2. So that's what happens when you have a horizontal translation. It's the opposite of that inside sign. We're going to come up with a formula for that, but for now, those are some things that you can start to see. So now, I'm not even going to graph this table. I'm going to say, I wonder if I can just take the parent with the, let's go with the vertex that I talked about. The vertex is this bottom point where it doesn't have a symmetrical, and I'm going to shift it to the right 1, 2, 3. 1, 2, 3. Then, without any other transformation, I can do that up 1 over 1, up 2, up 4, because 2 squared is 4. I'm going to be off the grid again, so I'm just going to connect. Now let's say I still was struggling here. You are always welcome to use your graphing calculator. So to plot this in your table, you would say y equals parentheses x minus 3, close parentheses, squared has its own key. If you're going to use a calculator, you have to know how to use the calculator too. Okay? It's only as good as you are. So if I graph it, I can see the picture. But let's say it was a quiz question that was asking me for an exact output and I was unsure. Okay? Even though I know you're all super smart and you would plug that in. -3 minus 3 is -6, squared is 36. But let's check by hitting the table. When you want to get to the table on the graphing calculator, you hit second table. And there you have it. So the output at -3 is 36. The output at -2 is 25. -1, 16. 0, 9, etc. And I'm just getting those. If you didn't have a calculator and you didn't understand the way I sort of did it ourselves, you just plug this in here. So 1, for example, minus 3 squared is -2 squared is 4. So you can always, always, always plug it in. You can think about it. You can graph it. As we get more into Math 2, it's so exciting because you've got so many things that you can do, you can access. So for equations in the form y equals x minus h squared, the graph is the same size as y equals x squared, and it is shifted h units, I'm going to put that in quotes, in the opposite direction of the sign. Now I'm going to be out of the box. I hope I'm not off the grid, but I probably am. I don't have kids here to yell at me. Okay. So again, I want you to pause the video there. We may even end. It depends on my time. We took a brief interruption so we can review square roots of perfect squares. As you can tell where we're headed, it's all about that parent graph, y equals x squared. So you have to know how to take the square root of a number. Now if it's perfect, square root of 36 is 6. The square root of 64 is 8. The square root of x squared is x. The square root of x to the 4th is x to the 2nd. Now, I know Math 1, some of you came and went and we had a wonky spring, but let's review perfect squares. If they're numbers, 1 squared is 1, 2 squared, 3 squared, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We could keep going, but we won't. So you should know perfect squares through 15. It'll make your life way easier. And sometimes we have no calculator quizzes. But when they're polynomials, it's an even number. So x squared square root is x, because x times x is x squared. So when you take the square root of the number, it's what number times itself. So x to the 6th square root is x cubed times x cubed. So when you multiply exponents, you add their powers. So this is going to be key when we factor. This is why we have to review a little bit of radicals. Okay, so the Square root of x to the 6th is x to the 3rd. So if it's an even power, you just chop it in half. Square root of 16 is 4. Even power, chop it in half. So the square root of a number we have to know, but even power, chop it, chop it. Square root of 100 is 10. Chop it, chop it. Okay? So that's what you're thinking, that y to the 4th times y to the 4th is y to the 8th. So we add the power. So when you take the square root, you actually are going to divide. So again, try to be good to yourself. Pause the video. Try these next 4. And then I'll see you. And you're back. Okay? So the square root of y squared is y. The square root of z squared is z. The square root of delta squared is delta. These are just shapes, just to kind of get you to think about it. This is just a shape, if you will. This is just like they undo each other. So all I'm left with is 36 minus 49. Don't turn around and take the square root of that. That would be like a double square root. So, you know, these can get tricky quickly. So just do, like I'm taking the square root of 4, the square root of x squared, and then the square root of that parentheses. Just to kind of be dramatic. Now, will we have them like this? Not just yet. This is just to make sure that you understand so that when we factor and we take the square root of a polynomial, you're good to go. Okay, so this may be the end of our day 1. We'll see. I have to put this all together. Alrighty, so Optima thought that that last situation was very tricky, and she hoped that multiplication was going to be straightforward. She decides to start simple and multiply by -1. So she begins comparing y equals x squared and y equals the opposite of x squared. Use your calculator to generate the graphs. Okay, you're getting to be an expert at y equals x squared because that is called the... Hopefully you're all shouting, parent graph. Okay, so that's y equals x squared. And you could probably imagine, even before I graph it, second quit, y equals, clear out whatever you have, minus x squared is going to flip it upside down. That's called a reflection. That's called a reflection. Optima is encouraged because that one was easy. She decides to end her investigation for the day, oopsies, sorry about that, by determining the effect of a multiplier, a, in the equation y equals ax squared. Use your calculator to graph each of the following functions one at a time on the same graph as y equals x squared. How does each one change from y equals x squared? Okay, so we're just, if you want to pause here and answer for yourself, if it's skinnier, wider, reflection, and it can have more than one transformation. So hopefully you're back now. This would make it skinnier, and it opens up. Why does it open up? Because 3 is positive. This would make it super skinny. It's not the best math word. That's a vertical stretch. And opening down is a reflection. If we want to be mathematical. We haven't seen one like that on the graph. That was the example I gave that I just sort of tossed at you. So this is going to make it wider. And if you think about it, something that grows a third as fast, it's going to be not so fast. And this is going to open up. because it's positive. This is negative, means it's going to open down. And it's also going to be wider. In general, for equations in the form y equals ax squared, if a is greater than 0, which is a fancy way to say it's positive, the parabola opens up. If a is less than 0, the parabola opens down. If the absolute value of a is greater than 1, so what that is saying, the absolute value, is that no matter if the number is positive or negative, it's going to make the parabola skinnier if it's bigger than 1, and if it's less than 1, it's going to be wider. Sometimes I'll sneak in like a 0 because I don't want you to think. Sometimes that's easier for people to see this as a fraction, but that's how you'll see it in a textbook. So I suppose I should be legit. All right. If you ever pick up a math book. Because we use all MVP, PDFs, whatever. Parabola is wider, and if it's equal to 1, the parabola is the same size. And what is it the same size as? The parent graph. Okay. Okay, and finally, on this probably 2-day lecture, other information about the graphs of quadratic equations. All right, so I think I'll go with, a pencil's hard to see. I just want you to know I would normally always use pencil, but it's not a very good way. I guess I'll just use this black one. Okay. So this parabola is opening down. Okay, so that tells me that a is negative. So as you start to look at parabolas in Module 2, we want you to always compare it to the parent graph. So I already know that a is negative. That point that I talked about, hopefully you remember what that's called, a vertex. And that is at 1, 2, 1, 2, 3. Now, since it's happening at the top of this graph, I hope that you can intuitively call that a maximum. So we say that the vertex is at a maximum when it is on the top of that parabola. This line that I cut right down the middle at x equals 2, remember a vertical line is x equals. That is called the line of symmetry. Now, the line of symmetry is always, I'll try to print, halfway between the x-intercepts. Okay. So this parabola is opening up. I'm going to draw in that line of symmetry. That line of symmetry is at x equals -3. This vertex, now I'm just looking at the graph here. The vertex is at a minimum. Why is it at a minimum? Because it's on the bottom. And the vertex in this case is -3, -1. So this is an ordered pair. this is a line. Okay. So I would encourage you pausing the video and just kind of writing down some identifying information about this graph. Welcome back. Hopefully you answered, where is the line of symmetry? Okay. Now, now this is kind of going backwards. So this line of symmetry is going to be right down the middle. If you folded this parabola in half, that line of symmetry would be halfway between the x-intercepts. So this is what I mentioned up here. The line of symmetry is halfway between the x-intercepts. Well, this x-intercept is -3, and this x-intercept is 6. So -3 plus 6 is 3. So this line is x equals 3/2. And if you said it's x equals 1.5, that's okay there. We're not at slope anymore. Try to kind of get in the habit of just keeping a fraction. Fractions are, you know, just easier. Then you don't have to worry about rounding. But anyhow, too. What we'll come up with later, if we're looking for the vertex, is 3/2 something. And that, my friends, is coming soon to a math video lecture near you. Aka love. Do your homework.